This short video will cover the material in sections 115 and 116, and this is the end of cycle 1. So section 1.15 covers social change, and we're going to talk about linear and exponential change. So in your textbook, there is a box here that explains what a function is, and a function is a rule that assigns a value of the independent variable, known as an input, to exactly one value of the dependent variable, which we call the output. And if you look at the example provided here, we're looking at the number of hours worked in a week relative to the salary that somebody makes. And we look at a graph of the data, and obviously the hours is going to be the independent variable, the one that influences the other variable, and the dependent variable is the salary. And in fact, here's the equation of this function. It's number of hours times 1575, which is actually the hourly salary. So we're often presented with a situation or a problem that we want to understand better, and what mathematicians do is a process called modeling, where we try to determine the relationship between the variables involved in the particular situation. And so we're going to look at different ways to model in this section. So suppose the owner of a new company has the goal of gaining 500 new customers each quarter. We want to write a function to model this that shows the relationship between the number of quarters and the total number of customers. And we can use a table, a graph, or an equation. And one thing we're interested in is what would they expect to have after 5 years, and how long would it take this company to gain 100,000 total customers. So we can do a table, again, a graph, or an equation. And in this situation, we're going to look at all three to see which one best represents it. We're going to start with no time because the company has no customers. And then in each quarter moving forward, the number of customers is going to increase by 500. So here's a table. So in the first quarter, they have no customers. Move to the next quarter, quarter 1, they've gained 500 customers. So each time the quarter goes up by 1, they gain 500 customers. And so here's the relationship that we're looking at here. We're looking at the number of customers is equal to 500 times the number of quarters. And then we can graph this. And we can connect the points here. Look at this nice graph. It's a nice linear relationship, as we see. As the increase through the quarters, the number of customers continues to increase by, again, 500 per quarter. And we can label the expression for the nth term of the total sequence as the number of customers, and that's again that equation that we get. The number of customers after n quarters is 500 times the number of quarters. Notice in the table, each output is 500 times the corresponding input, which confirms the relationship that we just wrote here. This equation can be used to find the number of total customers after 5 years, which is 20 quarters. So if we substitute 20 in for n, we see we have 10,000 customers after 5 years. And then we also wanted to know how long would it take us to get to 100,000 customers. And so we're going to solve the equation here, put the number of customers in as 100,000, divide by 500 per quarter to find out the number of quarters. 200 quarters, which actually translates to 50 years. So adding 500 customers a quarter is not a terrific way to increase the number of customers. This is a lengthy process, and we're going to look at some other ways that a company might gain customers more quickly. And just to summarize, what we just talked about is called linear function. Linear function is a function whose outputs increase or decrease by the same constant amount each time period. And if it's increasing, we call it linear growth. If there's a decrease, we call it linear decay. And the basic form of a linear relationship is going to be the dependent variables equal to some starting value plus the rate of change times whatever the independent variable is. And here's what they look like when we graph them. Here's linear growth, and here's linear decay. Use the following data to determine if it's a linear function of x, and if it is, let's write an equation to model it. So if we look at the relationship we see here, x is going up by 1 each time, or each period. And what's happening in y? It's changing by what? It's going up by 6 each time. So this is what we call a linear relationship. They increase by 6 as the x values go up by 1. And we can write that like that. Remember, it's the starting value, negative 18, plus the change, which is 6 per period, times x. Let's try another example. You have an interest-free loan of $800, and you're paying it off at $50 per month. Model the situation with a table, graph, and equation. First of all, is it linear? Yes, it's linear because you're decreasing by $50 per month, Here's the way the relationship is written: where we started, $800, subtracting, because we're paying it down, $50 per month. How many months will it take to repay the loan? It'll take 16 months. How did I figure that out? I want to have the amount be 0. I substitute 0 for the amount and solve for m, and I'll come out with 16 months. And here's a graph. So linear functions are useful when we're looking at things where we have constant or consistent changes. But sometimes we have a change that's a multiplicative factor or a percentage. And those are commonly found, especially in business. So let's look at this example, and also here in medicine. A virus is contracted by 100 people, each of whom infects 2 more people the first day, after which they're no longer contagious. We want to write a function to model the number of new people infected each day by the virus. Assume that the infection will continue to spread from each sick person to 2 additional people. We want to use, again, a table, graph, or equation to determine how many people will be infected on the 14th day. And then also, when do we get to 100,000 infected people? So let's start small for this one. So let's start with just 1 person, and then we'll scale it up to 100 people. So if we have 1 person on the first day infected on day 0, and that person infects 2 people, and then on day 1, each of those 2 people infects 2 people, and on day 2, each of those 2 people infects 2 people. And so we see here that we have a rate of change that's different from what we saw before. We're not adding 1 person each day. We're actually doing a multiplicative. We're doubling each day. This is actually called a geometric sequence, but we can also write this in a table. So on day 0, we had, let's scale it up to 100 people. We have 100 people. Each of them infects 2 people, so we're going to multiply by 2, multiply by 2, multiply by 2, and so forth down the table. And in a minute we'll talk about this general form here. And look at the graph. It's not a straight line. It starts off very slowly, and then once it takes off, it really increases quickly. And we'll label the term for the nth expression, for the nth term of the sequence as the number of people infected. And the equation formed is another way to represent the function, and here's how we do it. Okay, when it's going to be called an exponential function, what we started with. And now instead of adding here, we're going to multiply times whatever the change factor is. Here it was doubling, times n. In this case, n is the number of days. Notice in the table, each output is 100, the value of 2 raised to the corresponding input, which confirms the result. And we can find on the 14th day how many people would be infected. So I'm going to substitute 14 for n. And in my order of operations, I'm going to do this portion first and then multiply by 100. So in 2 weeks, we've got more than 1.6 million people infected, which is a very rapid rate of change. If you remember in the last example, where we'll be adding 500 customers per quarter, it was taking a long time to get to 100,000. So exponential function is a function whose outputs experience a constant multiplier as the inputs increase by 1. And like we had with linear, we can have exponential growth or exponential decay. And again, here's the basic form. The dependent variable is equal to the starting value times whatever the multiplier is raised to the independent variable, which is usually some type of a time parameter. And here's what the graphs look like: exponential growth, exponential decay. So let's finish with this example here. City planners for a city with a current population of 100,000 are modeling the population in various ways to help them make decisions related to resources. Experts disagree on the growth rate and model since they're using different data, but they do know they have resources for only 200,000. For each scenario, write a function. Okay, first one is the population increases by 500 residents per year. So a constant rate of change, so we're going to have a linear relationship here. Where did we start? 100,000 plus 5,000 times n, where n is the number of years. This time we're going to increase by 8,500 residents per year. So again, a linear relationship, 100,000 where we started, plus 8,500 per year times the number of years. Population increases by 2.5% per year. Now notice this has gone back to the multipliers we talked about earlier in the course. If I'm starting at 100 and adding 2.5%, I get to 102.5%, so my multiplier is 1.025. Again, initial value times the multiplier raised to, in this case, the number of years. And then lastly, if the population increases by 3% per year. Again, I'm going to use a multiplier of 1.03, initial value, and 1.03 is raised to n, where n is the number of years. Alright, and the last section in the first cycle is on area and perimeter. And just a definition first, area of a two-dimensional figure is the size of the region enclosed by the figure. It's measured in square units. Perimeter is the distance around the figure, and this is measured in what we call linear, or just the units of length. There is a handout in my courses with commonly used formulas. I would urge you to use those formulas rather than trying to read the blocks off the grid. I think it's easier to use the formulas. So the first thing I need to know is, what kind of a figure is this? This is a trapezoid, and the formula for the area of the trapezoid is 1/2. B1 and B2 are the two bases, the faces that are parallel. Base 1, base 2, times the height. And in this figure, I'm going to find B1 and B2. B1 is 4, B2 is 6, and the height is 4. Substitute in, and the area of this figure is 20 square units. A right triangle has sides of 10, 24, and 26. What is the area of the triangle? I would draw a picture to orient myself. Right triangle means there's a right angle, and the longest side, the hypotenuse, is the side opposite that angle. So now I can see, and remember the formula for a triangle is 1/2 the base times the height. So I'm going to find B, 24, height 10, and I come up with 120 square units for that figure. And then the last concept in this section is what we call similar figures. If two figures are similar, they have the same shape but not necessarily the same size, but the ratios of the corresponding sides are the same. So if we look at, and these are oriented in a different fashion, so I just wanted to show that to you. This one's kind of flipped when we go to the other one here. But all the ratios are going to be the same. So if we take in this figure, this 12 here corresponds to the 6. 12 over 6 is the same as the ratio of 24 to 12. It's actually 2 to 1. And let's try one example with this one. The following triangles are similar. Find the lengths of the remaining two sides of the larger triangle. Alright, so I'm going to take, first of all I'm going to set up my ratios. So 5.7 is to 3, and I'm going to find x is to 5. Cross multiply and solve. Cross multiply, solve for x, and I get 9.5. So this side here is 9.5. And then I want to solve for the other side, the longest side. So I'm going to take the same ratio here, and then I'm going to set this up, x as y is to 6. Cross multiply and solve. So now I find this side is 9.5 and this side is 11.4. And one last definition in this section, figures with the same shape but not necessarily the same size are similar, but if they have the exact same size and shape, we call those figures congruent.